Hi, my name is Nuno Faria. I'm a researcher from Inesctec University of Minho, in Portugal, and I'll be presenting TIC, which is a proposal to improve the transactional performance of analytical systems for hybrid workloads. Traditional database systems were primarily designed for operational or OLTP workloads, where we usually have read and write operations that only access a small number of rows and must be executed in an atomically and isolated manner. The transaction isolation is implemented directly with a row-oriented storage manager, and queries execute over this abstraction. The traditional architecture has, however, limitations when it comes to analytical or OLAP workloads, where queries that process large sets of data are executed. This has led to the creation of specialized systems designed specifically for analytical workloads, which rely on column-oriented storage and data processing techniques such as vectorization, adaptive indexing, and parallelized execution. However, fast analytical performance is often achieved by sacrificing operational performance or by not even supporting transactional workloads. Some use cases do require both high transactional throughput with fast analytical execution time, in what is known as hybrid transaction analytical processing, or HTAP for short. One way to achieve this is by having two specialized systems and replicating data from the OLTP to the OLAP store. The problem with this approach is that there is a delay between the analytical and transactional data, which is not ideal for real-time analytics, and also managing multiple systems incurs higher operational costs. Another way is having multiple copies of the data in the same system, possibly in different formats, to avoid mixing transactional data with long-lived analytical queries. This, however, leads to higher storage requirements and can also cause delays between the analytical and operational data, depending on how the copies are maintained. Finally, another option is to use the same data for both workloads, but building a specialized transactional storage engine. This is the best approach in terms of data freshness, but requires an efficient transactional storage manager to handle both workloads, which is both costly to implement and maintain, and more difficult to adapt to diverse isolation criteria, given it requires changes to critical, low-level components. Our approach to HTAP is transactions in the query engine, or TIC for short. Just like the last approach, we only have one copy of the data. However, instead of building the transaction isolation directly in the storage manager, we build it through high-level queries and procedures. Any required metadata is stored directly in the database with additional tables and columns. To implement multi-row transactions, the only guarantees required by TIC from the underlying storage engine are atomic single-row reads and writes. Our first hypothesis is that by leveraging the flexibility of an optimizing query engine, we can easily offer multi-row transactional isolation to existing systems with efficient query engines, not requiring low-level changes to the underlying storage manager. This also makes it easier to support a wider range of isolation criteria, which can be set depending on the application needs. Our second hypothesis is that transactional operations, such as computing the snapshot or certifying write sets, are themselves complex data processing tasks. Since the transaction isolation is optimized together with the workload, it can take advantage of data processing techniques such as vectorization and parallelism, and even be tunable by the administrator. The idea in TIC is for the client to execute operations based on the original schema, without knowing the TIC details. These operations are sent to the abstraction layer, which translates them based on the isolation criteria. This translation layer can be implemented with a client-side driver or, if the system supports it, directly in the database interface by using techniques such as views or rules. The resulting queries are then sent to the physical layer, or in other words, the underlying database system, to be optimized and executed. This layer contains, in addition to the application data, metadata, such as timestamps and sequences, required by TIC. To support transactional isolation through the query engine, we must make changes to the application schema. A schema in TIC will include two main types of tables. The storage tables, which store application data contained in the history of every current and future transaction. This means that we don't need to add metadata to these rows, and thus they have the same schema as the original tables, and the cache tables, which store uncommitted or recently committed data. They have extra columns to include transactional metadata, namely if the row is deleted and the respective transaction identifier. The main reason we do this separation is to reduce the storage overhead required to implement TIC. Additionally, if the system supports multiple storage formats, another advantage is that we can store the storage tables in column format for fast reads and the cache tables in row format for fast writes. We also have the TXN table, which stores main information about the transactions, namely the identifier, the start and commit timestamps, and the current status. Finally, to assign identifiers and starting and commit timestamps to transactions, we also consider the existence of the TXID, the STS, and the CTS sequences, respectively. TIC considers four main types of operations: begin, read, write, and commit. Transactions in TIC execute under optimistic guarantees, meaning they write without acquiring any locks and, at commit time, are certified to deal with any potential conflicts. This eases the implementation effort since we don't have to implement a lock manager. We also choose snapshot isolation as our target isolation, since this means that reads can execute without blocking writes, which is especially useful for hybrid workloads where we have long-running analytical queries. Starting with the begin operation, it assigns transactions a unique identifier and the current timestamp as its starting timestamp. This timestamp will be used for computing the snapshot as well as identifying conflicts on commit. In this example, since the current TXID sequence is 3, the transaction will receive the unique identifier 4, and the sequence value will be incremented. Additionally, its starting timestamp will be 3, according to the current visible timestamp stored in the STS sequence. To compute the snapshot for reading, we combine the storage, cache, and TXN tables with a SQL query, which can be offered as a view if the system supports it. One way we can specify this operation is with the following code. We combine the storage data with the visible cache data. We then order versions of the same row by timestamp, ensuring that the storage data is ordered after the cache data, since the latter is always more recent. Then, we select only the most recent version of each row. And finally, we discard the deleted rows and project only the application data. In this example, the resulting snapshot will contain the rows A1 and B2 from the storage and D4 from the cache. The C3 row in the storage was replaced by a version in the cache. However, this version is not in the final snapshot, given it was marked as deleted. Finally, the snapshot contains D4 and not D40, since D40 belongs to a non-committed transaction. One thing to note about reads is that both the snapshot code and the application query are optimized as a whole. For example, selections can be pushed down directly to the source tables, as shown here, where we want to filter table T by k equals x. We can see that the k equals x selection is pushed directly to the storage and cache tables, minimizing data materialization and exploiting available indexes. As for writes, we convert inserts, updates, and deletes into new inserts to the cache table, along with the respective metadata. For example, consider that we want to multiply by 10 the value with k equals a. Since the current value is 1, we insert in the cache table a value of 10. We also set the deleted column as false, since this was an update, and mark the row with the transaction identifier, which in this case is 4. Just like reads, writes can be translated with the database driver, and additionally, if the system supports updatable views, we can also rewrite them using rules. For example, in the following PostGres rule, updates are redirected as new inserts to the respective cache table. Finally, to commit a transaction, we start by assigning a commit timestamp. In this case, as the current commit sequence value is 3, the assigned commit timestamp will be 4, and the sequence will be incremented. Then, we validate the transaction's write set to check if there are write conflicts using the following query. This query checks if the transaction's write set intersects with the write set of all the transactions that committed while it was running. If the intersection is a non-empty set, the transaction is aborted. Otherwise, we repeat the process for the remaining tables. Notice that we only check for conflicts in the cache tables, since the data in the storage tables are guaranteed to be committed before the transaction started, reducing the complexity of the certification step. Using the previous example, the only written data is a row with key A. Since there were no concurrent modifications made to this key, the transaction can commit. Its stats will be updated to T, and the STS sequence will be incremented to 4, to make this data visible to future transactions. The problem with the optimistic execution is that it can cause starvation of long-running update transactions, as they can keep continuously conflicting with smaller transactions that finish first. To mitigate this problem, Tick also supports a priority flag to order a transaction before others, even if they try to commit first. In addition to improving long-running transactions, this shows the flexibility of Tick to implement optimization techniques without having to code them in the storage engine itself. The last two design points concern checkpointing and recovery. Periodically, data including the history of every current and future transaction are moved to the storage. This process, called checkpoint, is aimed at reducing the storage overhead as well as the complexity of the snapshot computation by keeping cache tables relatively small. It also garbage collects writes of aborted transactions. In this example, the minimum timestamp readable by every current and future transaction is 3, because there is one running transaction with 3 as its starting timestamp. We use this value in order to determine which cache data can be moved to the storage, represented here by lambda. The first row is moved to the storage as its commit timestamp is less than lambda. The next row will replace the previous version in the storage. However, it won't be stored there since it was marked as deleted. As such, we only have to remove the previous version from the storage. The next row cannot be checkpointed since it belongs to a non-committed transaction. And finally, the last row cannot also be checkpointed given its commit timestamp is greater than lambda. Checkpointing this row could lead to non-repeatable read anomalies since transaction 3 can still read the version in the storage. One key aspect of checkpointing is that it doesn't require multi-row atomicity. We can move data row by row and still ensure consistency. This is because a row is guaranteed to either be in the cache, in the storage, or in both. In this last case, the snapshot computation is already designed to discard duplicates. This is important because checkpointing can therefore run in the background without interfering with the foreground workload. As for the recovery, when the system restarts after a crash, we look at the TXN table and mark incomplete transactions as aborted by updating the respective status. This prevents them from being readable by future transactions or flushed to the storage. Additionally, we also have to update the visible timestamp to include the last committed transaction. We implemented Tick with MoneyDB, which is a state-of-the-art analytical SQL system. MoneyDB stores data in the column format, both when in disk and in memory, and supports features such as advanced query parallelism and vectorization. To adapt Tick to MoneyDB, we made the following decisions. We avoid updates, since MoneyDB triggers conflicts on concurrent updates in the same column. This means that instead of having just one TXN table and updating it as the status changes, we have one TXN table for each status. Sequences are implemented to MoneyDB's user-defined functions using pthreads. Writes are buffered client-side to reduce the number of round trips to the database in a transaction. We have an additional relation that contains the right set keys of the entire transaction, independently of the table. This means that we can certify a transaction with a single query, instead of having a query per table modified. Ephemeral data is stored using unlocked tables, meaning they are not flushed to disk. And finally, due to a MoneyDB bug, which has since been fixed, multi-column primary keys are modeled using an extra column which concatenates their value to make selections faster. We will now show some selected results that evaluate the implementation of Tick on MoneyDB. We have here three types of tests. First, we test the performance improvements in operation workloads, and to do so, we rely on the widely used TPCC benchmark. Then, we test the impact on OLAP, and for this, we use the CH benchmark, which are TPCH queries adapted to the TPCC schema. And finally, we test the performance of executing OLTP and OLAP workloads concurrently. Starting with the OLTP results, we have plotted on the left the average throughput based on the number of clients used, while on the right, we have the abort rate. We can see that Tick does indeed improve the transactional performance of MoneyDB, and this is mainly due to the fact that Tick operates on a finer-grained conflict detection than the native MoneyDB. This is clearly visible in the abort rate chart, where you see that native MoneyDB is already at 50% rollback probability with just 2 clients. Additionally, Tick behaves similarly to the state-of-the-art HTAP system single store and TDB, even slightly outperforming them. Meanwhile, Postgres, the traditional role-based system, achieves the best transactional performance, as we expected. Looking now at the OLAP results, we have here on the left the total response time of executing the 22 CH benchmark queries, and on the right, the individual time for each one. We see that Tick snapshot computation incurs some overhead over the native MoneyDB, of around 20%. However, when we consider the improvements on the operational workloads of several orders of magnitude, this is a good trade-off for hybrid workloads. We also see that Tick again achieves a similar performance to single store and TDB. Finally, Postgres now has the slowest performance, and this is because the raw format will require more data to be moved across the memory hierarchy, unlike the other systems. Finally, we evaluate the performance impact of each workload on the other. The test on the left plots the average throughput of 6 fixed operational clients based on an increasing analytical load. Conversely, the test on the right shows the analytical response time of 6 fixed analytical clients based on an increasing operational load. The CPU resources are divided in such a way to ensure that both workloads do not need to contend for them. The left test shows that Tick suffers only a small decrease in operation throughput with the increasing analytical load. The main reason for this is that although the workloads do not share compute time, they still have to share CPU cache, which is relatively small compared to the amount of data being processed. We also see that THTAP systems also behave similarly to Tick. On the other hand, Postgres has a good transactional performance without any analytical clients, but quickly decreases to half with just a single analytical client. After 2 clients, it even achieves a lower transactional performance than Tick. Switching to the right test, we see that all column and format systems have a similar response time and behave equally with the increasing operational load. On the other hand, Postgres has the highest response time, which slowly increases with increasing OLTP load. Both these tests demonstrate that analytical workloads on Tick have little impact on operational workloads, and vice versa, which are essential properties to have in HTAP systems. To finish this presentation, here are the main takeaway points. Transactional operations, such as reconstructing the visible snapshot and performing conflict detection, are themselves complex data processing operations that can be optimized with a workload in the query engine. Query-level transaction isolation makes it easier to build on top of existing systems, since it does not require changes to low-level code. Tick's flexibility allows custom isolation criteria. For example, analytical operations can be executed over an old snapshot to improve performance, or you can also have non-transactional tables that bypass the snapshot computation and conflict detection procedures altogether. And finally, we managed to improve MoneyDB's transactional performance with a relatively little impact on analytical workloads, bringing MoneyDB closer to state-of-the-art HTAP systems. Thank you for watching this presentation about Tick. If you'd like to know more, you can check out our repository, which contains the full paper and the code used.